Hello, everyone. Welcome to today's Happy Maths Hour. More on Pythagoras. This time, we're going to be looking at the man himself, Leonardo da Vinci's Pythagorean proof. Tony.
Well, yes, over the last few weeks, we've been talking about this theorem. And here's a picture in the middle of the screen now, apart from Caroline's pretty face and me talking to a little boy in the classroom in South Africa. In the middle of the screen, you can see a diagram, which is Leonardo da Vinci's way of proving this theorem. What is this theorem? What is it? Well, here we are. This is the theorem. The area of the square on the hypotenuse is equal to the sum of the areas of the squares on the other two sides. And that's called...
Well, we've done that, haven't we?
Yes, of course we have. It's the Goo-Goo theorem, isn't it?
Right. Yeah, the Goo-Goo theorem. Sorry.
Yeah. Well,
I think of the Guggenheim Museum whenever you say that.
Yes. Well, that's what my terrible pronunciation of Chinese is what the Chinese call it. And of course, it's much disputed about who proved this theorem first, but it's certainly not disputed that it was known, more than 1,000 years before Pythagoras. However, maybe you know it as Pythagoras' theorem. But
right, but we haven't proved that. We've gone through several proofs of that.
Of course we have. We're just chatting about it, and we'll see some more proofs. I'm just reminding people this might be
that. So there's more proofs. There's not just the ones we've done. There are more proofs.
Lots. And of course, this may be the first time anybody's joined our Happy Maths Hour. So what we're chatting about is here, shown you here, illustrated. Of course, you can read all that writing on that clay tablet, can't you?
Oh yeah, no problem whatsoever.
Well, I think you can see a right-angle triangle on it.
I can.
And the translation of that writing is 4 is the length and 5 is the diagonal. What is the breadth? Its size is not known. 4 times 4 is 16. 5 times 5 is 25. You take 16 from 25 and there remains 9. What times what shall I take in order to get 9? 3 times 3 is 9. 3 is the breadth. And that comes from a clay tablet found in Babylon, where Babylon was about 3,000 years ago. Okay.
That has to have been written by a teacher. That must have been a lesson.
Well, yes, but not in a classroom as we know a classroom today. And there on the right, there's another clay tablet from the same era with some diagrams on, which are clearly about right-angled triangles. And in fact, probably about how you prove the theorem. And there you see a picture from the Tupei Xuan Shang manuscript. And that was sort of more or less the same time as Pythagoras, but quite independent of Pythagoras, although there may have been some communication along the trade routes, which took the ideas one way or the other from east to west or west to east. And here is
how excited the mathematicians must have been to actually be able to communicate with each other.
Well, yes, but it wasn't direct communication as today. It took months and years for the ideas to be talked about here and talked about there.
During the Renaissance period, the mathematicians communicated by letter, which was taken by horse and cart. So sounds good
Caroline,
to me.
We had more than horse and cart, but when I was young, we communicated by letter. We put the letter in an envelope, stuck on a postage stamp, and you know, no emails.
I am old enough to remember those days as well. But yes. we also had the telephone, so we could communicate by telephone.
And so here we have the right-angled triangle with squares on each of the edges, and the theorem is that the bigger square is the sum of the areas of the two smaller squares. Now, there's a converse to this, and I put this up because I want us to be what they were certainly doing 1,000 years or more than 1,000 years before Pythagoras, was also in building using the converse of Pythagoras' theorem. That is, they took, say, 3, 4, 5 as a, 3 squared plus 4 squared equals 5 squared, which is what's written about on that Babylonian clay tablet. And they made a triangle with those dimensions, and then they knew the angle was a right angle. So they could use that to get an accurate right angle for building their walls vertical, or the corners of the room, with between two walls, to be exactly a right angle.
Rather than starting with a right angle triangle, they built edges of those dimensions, followed that rule, and then they knew they had a right angle triangle.
Exactly. So can you see that the theorem takes a right angle triangle and tells you that the bigger square is the sum of the two smaller squares.
Yeah.
And the converse says, if you know that a, b, and c are such that c squared is a squared plus b squared, then the angle opposite the edge, the longest edge, the edge C, is a right angle. So they get the right angle as a consequence. Okay. Now, just look back at that slide, and at the top right-hand corner where you see that Chinese, it's got Chinese writing on it, and vertically down on the left, although it's nearer to the clay tablet, it's actually Chinese writing.
Yeah.
Okay. Just focus on that. Now look at the next slide, and I've repeated it there. Okay.
Oh, yes. Okay.
And look to the right, and there is a colorful version, which we'll see in animation in a minute, of Pythagoras dissection, which we talked about last week.
Right.
But can you see it's different, slightly different sizes, and it's flipped over, but can you see that the two diagrams are the same?
Yes, you've got a little square in the middle, and you've got 4 right angled triangles that all end at the vertex of square C.
Yes, exactly. Yeah. So let's look, and as I say, that's the Gugu theorem. I'm sure that's not how you pronounce it, but I don't know.
To me. I like it.
Actually, my next door neighbors are Chinese. Next time I see them, I'll ask them to teach me to say it.
Yes, good plan. And then you can teach me. Thank you.
Yes, I don't promise to be able to say it, because I can't get the sing-song right for Chinese at all. I've tried with Chinese names and failed hopelessly.
Well, maybe you can record it on your phone and then send it to me so that I can pronounce, because
I'll do it. I'll do that, Caroline. Right, I'll do that. Okay. So watch this. This is what we just seen on the previous slide. Watch it.
So that's going across there, and that's going across there. So now we're only using the little pink square as a filler, basically. The two squares we're looking at are made up of, we're looking at the outline really of the area that's still made up with 4 right angle triangles, 4 congruent right angle triangles, and that little itty bitty square is literally just a filler, because they make a large triangle that's length B and a large square of length B and a smaller square of length A. So I can see those, even though I have to use a bit of imagination to do it, because it's such pretty colors.
The colors are a bit of a distraction, actually.
They are.
Yes. Yeah. So on the right, the upper one shows you the square on the hypotenuse of triangle. The triangle which has edges A, B, and C.
Yeah.
And in the picture below that, you see 4 right angle triangles and the pink square. But now what you see is the square on the shorter edge, the smaller one, and the square on the longer edge is the bigger square there. So you can see that this theorem holds. Well, it's one of the ways of showing that the theorem holds. Let's look at something else now. Sorry, I want to move on. Doesn't want to move on.
Gotta love technology.
Here we go. Now, here we've just got a picture for you to look at, and this is like a taster for our Leonardo da Vinci's proof. And here are the proofs that we have been talking about in the last few weeks. Well, an illustration of them. This was the first one that we did a couple of weeks ago, talked about, and Caroline used this with one of her classes of 14, 15-year-olds. This is yet another one. And actually, this is what we've just been talking about, but it doesn't have the pink square. It's shaded slightly differently. And there is a reminder of what we were just talking about, which has the pink square in, but you'll see it's exactly the same configuration as the one on the right above it. Yeah. So they're two animations, two different animations for the same thing. And here's yet another one, which has been attributed to Dewdney, but actually it was known long before Dewdney and probably hundreds of years before him.
And we did that a couple of weeks ago, didn't we?
Yes, we talked about all of these. Yes,
They're wonderful, especially when you do the animations. They're mesmerizing.
Well, yes, but they all, you do have to sort of think of it, because each one is subtly different, but they're all about the same theorem, and therefore there's a similarity between them.
Yeah, I mean, you can see the similarity between Perigles and Dewdneys very easily. It's just that one is kind of a truncated triangle made up of truncated triangles, and the other's the full right-angled triangles.
Well, the interesting thing about Dewdneys is that the pieces are made, the four pieces, which have got four colors there, are actually made by cutting up the middle-sized square, right?
Yes, yeah.
And then they're placed, but cutting it up in such a way as the right angles appear around the middle of the middle-sized square. And then those right angles are placed in the corners of the large square, that's the square on the hypotenuse, and the square remaining, which has got white stripes on black, is the smaller square. And so, yes.
So that one's made up. The square in the center is actually the smaller square, whereas Perigles, the square in the center is any square.
And the proof by areas, it's the four right angle triangles that go in the corner. So we've got different arrangements. And of course, as you see it there, Leonardo da Vinci's proof is again different. So this is the one which is what I call the proof by areas. And that we've got on our Aiming High website. And we started off with a jigsaw puzzle, which we call Make Squares, the Make Squares puzzle. And of course, it's obvious why it's making squares, because we make two squares there on the left and one big square on the right, but they're both in the same frame, A, B, C, D. And they've both got the four right angle triangles in, and what's remaining in the black there is either on the right the square on the hypotenuse, or on the left the other two squares. Okay, so if we go on there, we're going to talk a bit about Pythagorean triples again, because I've got a new fact here for you, Caroline. Okay, so just remember, if we've got whole numbers A, B, and C, right, positive integers, such that c squared equals a squared plus b squared. And of course, it can be true for any numbers. You don't have to have whole number measurements. But if you have got whole number measurements, there are lots of interesting things that you can do with them. Well, first of all, how would you find them? How would you find what we call a Pythagorean triple? These are whole numbers A, B, and C, such that c squared equals a squared plus b squared. Well, you take any two whole numbers m and n, right?
Wait a minute, stop. You said this the other day. Any two whole numbers. So I could have 1 and 756,223,000.
Yes, you could. Any
Wow.
whole numbers.
Okay,
But
cool.
I would prefer to do this with small numbers because the arithmetic is easier.
And you'd actually be able to draw it as well.
You might, yes. Okay, so so what you do is with your two numbers, which we're calling m and n, okay, you take m squared minus n squared, m
Okay.
squared plus n squared, and 2mn, and
Yeah.
they will be, believe me, always a Pythagorean triple. Okay.
Wow.
Now we
You
talked about
started with whole numbers, so you'll still have whole numbers because m and n are whole numbers.
and a little bit of elementary algebra will prove that c squared is a squared plus b squared always. Okay, so
That's
here's some
so cool.
examples. If m is 2 and n is 1,
Yeah.
m squared is 4 and n squared is 1. 4 minus 1 is 3, so that gives you one of the edges.
That's
Okay.
3 squared, yeah.
2 times 2 times 1 is 4, and that's another edge.
Yeah.
And 4 plus 1 is 5, and that's another edge. Okay.
Yep.
So there's one, and there's a picture of it. But you can do the same with m is 3 and n is 2. So 9 plus 4 is your 13. 9 minus 4 is your 5. And 2 times 3 times 2 is your 12. And there's a 5, 12, 13 triangle. And similarly, with M4 and N1, you can get an 8, 15, 17 triangle. Okay, so there's some examples. Now, we have talked about that and that you can draw infinitely many right-angled triangles with integer edge lengths. Okay, now I've got another very nice idea.
Okay, wait. You just kind of zoomed straight past that. An infinite amount of right-angled triangles. So does this prove that?
Yes, because you can take any values, as you just remarked, any values of m and n, and you will always produce a Pythagorean triple that way, and therefore a right-angled triangle whose edge lengths are all whole numbers.
Yeah, I never thought about. I always thought, well, there must be a limited amount of them. I suppose there are a limited amount of them in that, not a limited amount, but not every. You can't make a Pythagorean triple out of any three numbers, but you can make an infinite amount of right-angled triangles because infinity is infinity.
Well, yes, because I've just showed you the algebra there.
Yeah, I know.
You
but
use your m and n.
You're way high up there, Tony. Some of us are a bit
No, I'm
lower
not.
down.
No, I'm not.
Yes, you are. Yes, you are. Yes, you are. So the point is that you can, even though not every three numbers does it, if you do it in that configuration, you can find all the Pythagorean triples, and there's no end to the ones you have because there's no end to numbers. It's
Caroline, sweetie, there are lots and lots of infinities. Okay, there are an infinite number of right-angled triangles, and it's true for each of them that c squared is a squared plus b squared, but only for some of them are the edge lengths whole numbers. Okay.
Oh yeah,
but there are still infinitely many which have edge lengths that are whole numbers,
which is the amazing thing. Yeah,
exactly.
Right. So it boggles the mind. Okay, you can move on now. Sorry, I just had to really point that out because it got me.
Right.
Like, what?
Right.
No, can't be.
Now we just looked at the 3, 4, 5 triangle, and 4 is only one more than 3. Okay, you'll agree to that.
Yeah.
Are there other Pythagorean triples where the b is one more than a? Are there?
Surely not. I mean, it's just only the little ones because it's only 3, 4, 5. They're, surely not.
Let's have a look. So what about 20 squared plus 21 squared? That is 29 squared.
That sounds very counterintuitive.
Well, I don't see why. 400, because they're close to each other. The 21 is one more than the 20. 400 plus 441 is 841, which is 29 squared. Check it out. Okay. And I can show you how to find infinitely many like this. Okay. And here's the method. Are you ready?
I've got my brain switched on. My brain is
right. Now I've gone to big letters now to distinguish them from the small letters. And I could show you, just as we did with M and N on the last slide, with a capital A and a capital C here, I can show you that if you make capital A 2 little c plus 3a plus 1, and big C 3 little c plus 4a plus 2, you get one of these amazing different sort of Pythagorean triples. So let's try it.
A squared plus A plus 1 squared equals C squared.
Yes. Now let's do it with 3, 4, and 5. Okay. Yep. Right. So if we take our big, what would our big A be then?
Our big A is 2 times 5, so that's 10, plus 3 times 3, which is 9, plus 1, so it's 20.
Right.
Oh, that looks familiar. Okay.
Yeah. And what would our big C be?
Oh, I'm beginning to think that we're just basically scale modeling. That's okay. A big C is 3C, which is 15, plus 4A, which is 12, plus 2. What did I just say? 15 plus 12, 27, 29. Oh, 29. Look, there it is.
Yes, there you go. You've just done it.
And
okay.
A plus 1 is 21. So that we'd already, so 20 plus 1 is 21. Okay.
Now, if you go it again, right?
Then, and just keep going. Just keep doing
it again.
If you do it, and we have an infinite amount of numbers, so we can just
so 2A is 40. 2C, sorry, 2C is 58, plus what is it? 2C plus 3A is 60, plus 1, right? That gives you 119. And of course, A plus 1 is 120.
Well, of course, because by design they're consecutive, because that's how we've written the formula. So 119 squared plus 120 squared is...
Now, then your
13 squared.
Yes, so your big C was 3 little c, so that's 3 times 29, which is 87, plus 4a, which is 80, plus 2, and that gives you 169. Whoops, wow. And you get 119 squared plus 120 squared is 169. And
they are consecutive, and then you do it again, and their A and B are consecutive.
Yeah,
that is a real surprise to me, Tony. That is a genuine.
But it's only lower school algebra. There's no an arithmetic. There's nothing difficult about the algebra here.
Nothing difficult about it at all. It's just a surprise in terms of, for number one, Fermat stopped to think about it and work it out, but then it wasn't that difficult of a proof.
You can find infinitely many Pythagorean triples, A, B, and C, with B is just one more than A. That's what it is. Isn't it nice?
That's a nice. So that's another infinity within that. So it's an infinity within the. Yes. So we've got 3 versions of infinity here. One with integers, one with consecutive numbers, and a third one which is with any number. And we've got an infinite amount of all of them.
Yeah, but the bigger one is all of them. And then you've got the ones, then you've got the Pythagorean triples, and now we've got Pythagorean triples, the special cases where B is A plus 1.
That's fantastic.
You can go on. This is the area of maths which is called number theory, and a lot of it's very difficult maths, but some of it's like this is quite easy. But it's a whole branch. There's been a whole branch of research, and number theorists like to stick to the numbers and not be have their very pure mathematics tainted by anything else, not geometrical pictures or anything like that. But modern mathematics tends to now look at all mathematics and look at it from all directions. Okay, let's move on. So now what we're moving on is to see this. We saw it earlier this afternoon, but we're just having another look at it.
Yep, so
Okay.
you can see squares C and you can see squares A and B. So you're starting off with A and B, and then you're moving it across to square C. Okay, yeah, that's lovely.
Now
Watch that with A. Can we just sorry? Can we just spend 5 minutes watching that, Jenny? That's a joke. Okay, that's a joke. I do love it.
Yeah, I think these are all great, and the brilliant thing about them is that they only last less than a minute. You could show them if you're a teacher, you could show one of these at the beginning of the lesson, and you could ask children to talk about it. What do they think it means? Okay, and you could show it them without, in the middle of this, I've got c squared equals a squared plus b squared. Well, you could show it to them without showing them that, or you could give them the pieces that they could rearrange for themselves. And all right, so actually I'd like to do both, because I like to start a lesson with doing something. So I'd let the children watch it. I wouldn't tell them it was about Pythagoras' theorem. Okay. I would then give them the pieces and ask them to rearrange them in these two different ways. Okay. And I would then ask them to, that's the doing. Then I would ask them to talk about what they had just been doing and what does it mean? What can they get out of it? To write about it in their books. What do you notice? What does it mean? What do you think it proves? And draw the pictures in their books. So that's a do, talk, record lesson. Okay, so let's move on now. The next one is a different picture. Now,
that's the one you came up with before, Dudenese, where it's not triangles, they're actually quadrilaterals.
What? I don't see. What?
The little bits are quadrilaterals.
The bits are quadrilaterals. Yes, they are. Okay, so what you have got is the square on the hypotenuse, which is D, E, and then this is hidden under here, and then A. That one.
M. I think, was it B?
It's
B.
I think it's
B.
A, B,
A, B,
E, D, I think.
Yeah, A, B, D, E. Yeah, A, B, yeah.
And that was divided into 4 pieces by this line here, OM, and this one here, LN.
And that's very specifically cut at right angles. They're perpendicular. Those cuts where it's cut in.
Yes, and one copy of the triangle goes from here. Can you see the cursor moving round?
Hold on, no, wait. Where is it? Let me see. Oh, crikey! You can hardly see it because it's black on black. If you stay on the color, then
well, if we come down here, I'm just going around outside it.
Yeah.
And then I go across to N. Across to N there. Okay, well, shall I could play that again. It's very quick, though. So that's cut up into 4.
And it's intentionally cut into 4 right angles.
Yes, that's right.
That is a critical part of this proof.
Yes, and that you see produces 2 on the upper picture here, the square on the shorter edge of the square on the longer edge, which is the one that's cut up into 4 colored pieces, and the stripy one, which is the square on the shorter edge, and they are filled in on the square on the hypotenuse here.
Hold on, you said the square on the longer edge. Do you mean not the hypotenuse? So the hypotenuse is the one that's
Caroline, you call them, when we were talking about this before, you called this one the daddy, okay? The big one on the hypotenuse.
Yeah.
The mummy was the one that's cut up into 4 colored pieces.
Yeah.
And the baby is the stripy one.
Yeah.
Okay. Right. So now, Caroline, look at the right angle triangle ABC, which I've colored blue. And the squares, can you see the squares on the edges?
Hold on, I'm looking. Because I had to, it's a bit like an optical illusion. You have to kind of refocus. So give everybody a chance to refocus. Okay, because there's some other diagonals and things. Okay, I've got them. I've got the squares on the edges of the blue triangle ABC. I can see them. I'm ready.
Right, and they're ABGF.
Hold on, ABGF. Yeah, that's the mummy square.
The baby square is BCIH.
Okay, I see that, the little one. Yeah.
And the daddy square on the hypotenuse is AEJC.
Okay, AEJC. Okay, got it.
Right, so we've seen the squares. Now, AEDJ is another triangle, and it's drawn.
Hold on. AE.
No, sorry, I didn't say A. If I said A, I didn't mean to.
Sorry.
Triangle EDJ.
Hold on. EDJ. Oh, it's kind of stuck on the bottom of AEJC. So there's a triangle stuck on the bottom of the hypotenuse triangle, the hypotenuse square. Okay, that's stuck underneath. Got you.
And it's congruent to triangle ABC.
It's congruent to triangle ABC. Okay, so that is quite deliberate. It is a congruent triangle stuck on the bottom, but it's the other way around. It's rotated.
Yes.
Okay.
Now, FBI, actually, drawn through B, is a straight line.
FBI is a straight line. Okay, we've got that information.
And BD is a straight line.
BD is a straight line. Are they drawn to be perpendicular, or do we have to prove if they are perpendicular? Because they're going from a right angle to a right angle. And they are cutting that shape in half, because they have to be, because B to D, they're symmetrical. They've got rotational symmetry, so you must be cutting A, B, C, J, D, E in half.
Yes.
Am I jumping to false conclusions there, or is that?
Well, you're right about the I'm sure you're right about the rotational symmetry. So, but we'll come on to that a bit more in a minute.
Okay.
What can you say about triangle GBH?
GBH. Okay, that's above the blue triangle, and it joins the two smaller triangles, and so there's mirror symmetry there. That is a mirror image of triangle ABC, because all the edges are the same. It's also a right angle triangle, and so it's congruent again with ABC and EDJ.
I can't resist this. If I coloured it blue, we'd see a blue butterfly there.
Yeah, that's lovely. Also, I'll tell you what else you can see, Tony. No, I'm wrong. I was going to say, or is it? I was going to say that you would make a square if it was a piece of paper and the flaps were folded in. Would that make a square? No, I don't think it does. It doesn't. It doesn't.
I don't think, I can't see it. Caroline,
no, it doesn't.
Then shall we look at the two quadrilaterals up there? The ones GHIF.
Hold on. GHIF. Oh, okay. Yes, it's
and
the
ACIF.
It's like half of the butterfly. ACIF. So that they're two quadrilaterals that are formed by putting those diagonals in, and they're mirror images of each other.
They are those two quadrilaterals are mirror images, and the line FI is a mirror line or axis of symmetry, and so they're congruent. They're congruent to each other.
Okay.
Now we've got two more quadrilaterals. What can we say about those? So let's take the quadrilateral AEDB.
Hold on. AEDB. Well, that looks the same, but it looks as though it's going to be related. I think it's going to be congruent to AF If you rotate that quadrilateral with the axis of symmetry at A, if you rotate that, AB is going to be the same as FA. BD is going to be the same as FI. ED is the same as CI, and AE is the same as AC. So if you rotate that, it's the same. It's congruent.
Yes, I think if you rotate it through 90 degrees, if you take the center, we'll see this with colored ones in a minute, it'll be easier to see. But if you take B as the center of rotation.
B as the center of rotation. Okay, I was using A as the center of rotation, Tony, and then it literally rotates onto FAIC.
I'm not sure what rotates on. Oh, I see what you mean. You mean A, B, D, E.
Yeah.
Rotates to F, A, C, I.
Yeah.
If you take A as the center of rotation.
Yeah.
Okay. If you take B as the center of rotation,
okay,
and go anti-clockwise.
Anti-clockwise. Hold on, not that way. That way. So I'm going that way. Okay.
Take B as the center of rotation.
Yeah.
And I think you will find that CI rotates to oh, I'm getting stuck now. I think you get what you said, I think happens again. I'm going to stop there.
Okay, yeah, I'm not seeing it yet. So yeah, okay. All right. Well, you've got an animation though, haven't you, to help us?
We're going to look at an animation.
Okay.
Can you go? So we're going to see if we can go a bit further and prove the theorem. Okay.
Okay.
We've got a long way there. But before we do that, let's talk about this wonderful man, Leonardo da Vinci. I mean, he was perhaps one of the best artists that's ever lived. Certainly his Mona Lisa is hugely famous, but although he didn't paint as many pictures and as perhaps some of the other artists in history, he made some wonderful paintings, including his Last Supper, and there you've got the Virgin of the Rocks, and many others. But also he was an engineer, a scientist. He went into the theories of all sorts of ideas. One of his early ones was machines to drain the land, and of course architecture. And he drew the most wonderful plans, minute detail.
And
he was an architect.
Machines. He had vision for machines that could fly.
You can see some of his sketches there, flying machines, including a hot air balloon.
And I've actually seen them fly in Bognor Regis. They do an annual event where you fly off the pier. Well, there's a comical one, and I built just a silly one, I suppose. I built a version of Da Vinci's helicopter, which is based on a helical type shape, which doesn't work. But there was a team that actually built a flying Da Vinci, the hang glider version, and it actually flew. So and that's his design. They used his design. So yeah, it worked.
He's also supposed to be one of the first people to, if not the first, to think of a tank for war.
Yeah.
And in the picture on the bottom right, you see a scythed chariot with a man in the middle riding a horse, but in front and behind the horse is a scythe cutting the grass or something.
And you're wondering why the horse is leaping up. Help! What's going on?
Yes. And then he was also very interested in human anatomy and also anatomy of animals too. And there you see a picture of the fetus in the womb and other drawings around of human anatomy. And these drawings come from the Codex. Now, only a few years after Leonardo da Vinci died, his friends were very anxious that his manuscripts and his notebooks should be preserved. And this man, Pompeo Leone, he compiled a 12-volume, 1,119 page collection of Leonardo's drawings and writings. And here you see water wheels up on the right there. I chose the one on the below it because it showed some cones, and other drawings which show some conic sections. On the left, there's a horrendous looking war device, a big crossbow.
That's very scary looking.
And a flying ship with a barrel. Is that to take your water up? I don't know. Or is it just to give it weight? I don't know. Anyway, this is online now, this codex, and it was called the Codex Atlanticus, and there's a link to it. So if you want to try it, we'll show you we'll put all these links on YouTube, and it's got a wonderful search system, so you can it shows it's divided into sections according to whether it's architecture or art or human biology or physical science or whatever it was. And also, you know, you can search for different things, and you get these beautiful not depictions, actually. They are straight from Da Vinci's notebooks.
Fantastic.
Wonderful, aren't they?
That has got to be hours and hours and hours of intriguing
exploration.
Yeah, exploration. Talk about going into a rabbit hole. Would be hard to come out of there.
You could spend a day or longer on that, just looking at these wonderful things, and you can do it in the comfort of your own house, sitting, you know, with your computer, exploring it online. And here are some more. Interestingly, the one on the left, he's playing with this flower of life design, which we've talked about and before, and I use it as a depiction of somehow connections, many connections between people, and for AIMSEC as an image. Okay, so there's lots of
the middle
geometry.
One, I see early versions of the geodesic dome there. Looks like he was looking at building a dome, or is it?
Might have been. Might have been. If we could only read his writing, we might know a bit more.
Is this all mirror writing as well?
I think it was. That's what I've always thought. I've been told, yes. So there's some more pictures from the codex. Okay, now here is his proof. All right. So look at the two other copies of the same diagram, but colored in a different way. All right. Now, if you take the point which I think was labeled B before, can you see this point here?
Yeah.
And if you, as Caroline was saying, if you rotate, and I think Caroline rotated about, which point? Did you rotate about that point, Caroline? Anyway, you can rotate. I see what to do. If you rotate about this point here.
That's the one I did. Yeah, that one.
Yes, and you rotate clockwise. That pink quadrilateral rotates around to this position, doesn't it?
Do you want me to demonstrate it?
Oh, yes, please do.
Okay, so I've got that there. Hold on, I'm just going to put on my visualizer. So the plan is that I'm going to make it so we can see both the PowerPoint and what I'm doing. So we've got, let me just modify the lighting here. There, now. So this is what you've got. So I'm going to just remove this one and rotate this one about that point there. Hey presto. those weren't quite lined up. Now it's different, as in the shapes it's made from are different, but the outline is the same.
Yes, and of course the two top quadrilaterals that we saw are mirror images of each other. That's why Caroline had to turn it over to show you that they were the same shape.
I've got that here. This one here, I've got it in one piece, so you can see if I fold it over, they are mirror images along that line of symmetry. Okay.
Brilliant.
What else did we want to see?
I think that's it, Caroline.
There was something else, Tony. There was. You wanted to see this one was the rotational. Basically, it was a rotational version of that one. So if I just put those back in position. So that was the other one that we've seen, the top one, the one on the left on your, well, you can't see it, that one, it doesn't work, but the middle image is this one that I've just done. And now the one on the right is this one. So this one isn't a mirror, not a mirror image. What it is, it's a rotational. If I rotate this about this center point here by 180 degrees, it's the same. And the thing was, the final thing is as well that we've seen that this is the same as that. So all four quadrilaterals are congruent.
Absolutely. Now, if we look back at the PowerPoint, you can see that the top pieces here, right, are made up of two copies of the triangle, and the small square, which we call the baby square, and the middle-sized square, which we call the mummy square. But if you take away the two triangles, you're left with the two smaller squares. Whereas the bottom two here, right, are made up of the two triangles and the square on the hypotenuse, which you call the daddy square.
And it's the same two triangles, and the area.
So the area of these two squares, the small one and the middle-sized one, must be the same as the area of the larger square here.
Because you've removed the same two triangles which have the same area.
Yes. Okay. So that
with the two shapes that also have the same area, which we've proved because those quadrilaterals are congruent. This is incredible.
So now if you go back to the diagram on the left, you can probably see that for yourself. So you take two blue triangles away from the top piece, and you get the yellow square and the green square. And if you then ignore the top bit and you take the blue two triangles away from the hexagon, which is made up, as Caroline showed you, of two more copies of that quadrilateral. If you take the two blue triangles away, you're left with the purple square, which is the square on the hypotenuse. So now let's see this, and Caroline's going to show you this video.
Oh, hold on 1 second. One second.
Start with a right triangle with legs of length A and B and a hypotenuse of length C. The square drawn using the side of length A has an area of A squared. Similarly, the square drawn using the side of length B has an area of B squared, And finally, the square drawn using the hypotenuse of length c has an area of c squared. Then add 2 more copies of the right triangle, one reflected about the angle between the legs, and one rotated and shifted to the bottom of the square off of the hypotenuse. Next, we draw 2 lines of symmetry separating 2 hexagons inside of the diagram, like this. We use the new regions as follows. This top quadrilateral is congruent to its reflection along the first line of symmetry. The resulting quadrilateral is congruent to its rotation of 90 degrees clockwise about the left triangle vertex, and this quadrilateral is congruent by 180-degree rotation to the other half of the second hexagon cut by the second line of symmetry. Therefore, the 2 overlapping hexagons in the diagram are both built from 2 copies of the same quadrilateral. That means that these 2 hexagons thus enclose the exact same area. But notice that both of these hexagons use 2 copies of the original right triangle. So removing those triangles from both diagrams shows that the large square encloses the exact same area as the 2 smaller squares, which means that c squared is the same as a squared plus b squared. Remembering that a and b are the lengths of 2 legs of a right triangle with hypotenuse of length c, we have shown that for such a right triangle, c squared is equal to a squared plus b squared. This is the Pythagorean theorem as proved by da Vinci.
Isn't that beautiful? That is what we were just talking about, and I hope that made it clearer. So, Caroline, can you see my GeoGebra?
Not yet. Hold on 1 second. And it's now full screen, Tony.
Right. Can you see me moving the point?
Yep.
And it's making this, it's changing the shape of our right angle triangle. So it's exactly what we've been looking at. It's Leonardo da Vinci's proof. And as I make it about there, it almost appears to be maybe there. It almost appears to be an isosceles right angle triangle.
Yep.
But I can make it longer and thinner. Okay, or actually, I can move this other point here as well and change it like that. But always we have got the quadrilaterals that we had before. Okay, can you see? This is the 2 quadrilaterals with a sort of butterfly there, which is the which shows that this line is a line of symmetry.
Yeah.
And the 2 quadrilaterals here, which, as Caroline showed you, has rotational symmetry about here. The 2 quadrilaterals are the same.
Yeah.
And it's exactly Leonardo's configuration. I think that is so nice. So there you are. You see, and you can go to that GeoGebra proof. The link we will again give you that. Okay. And now back to my PowerPoint slide. And here is the link for you. It's www.geogebra.org. And if you just stop there and go to GeoGebra, you'll find, and then just search for Pythagoras Theorem, Leonardo da Vinci, you will find it. But we will also provide you with this this link as you see it on the page there. So you have seen this evening lots of different views of Pythagoras theorem proved in different ways. And then you see, I've been from habit calling it Pythagoras theorem, but I have also been at pains to show that it's, there are many other people who might have claimed, had they still been around, to say it was me. They were still around to put the hand up. They could have been, claimed to have been inventors of this theorem long before, or discoverers of this theorem long before Pythagoras. If you're especially keen, you could go to this website, which is called Cut the Knot. And that has got 122 proofs of Pythagoras.
Wait. I asked you earlier if there were more, and you said there were lots more. Well, that is a lot of proofs.
Well, they're online, and so you can find them. There it is, cutttheknot.org, Pythagoras, and there they all are. But there was a book written in, I think it was 1917, about just over 100 years ago, which had more than 200 different proofs,
Wow.
and there are more than that. So,
Wow.
but they're subtle variations of each other, and I think, you know, it's quite interesting to see the similarities and the differences between these proofs. So we've just been chatting away. Last week we talked about Perigal, Henry Perigal, and he only lived about 100, he lived in the 19th century, and we've gone a little further back in time to Leonardo da Vinci today. But over this last 4 weeks, we've been hopping around through the, well, thousands of years where this theorem has been talked about. It's also very important when it comes to the distance formula for the distance between 2 points, which is actually completely based on this theorem. And then we might talk next week about, that's the distance in Euclidean geometry, which you'll recognize, but we might talk about how the distance formula in other geometries, in spherical geometry and hyperbolic geometry, and there is a distance formula.
Just to let you know, the spherical geometry is like the geometry around a sphere. That's kind of obvious. Hyperbolic is if you imagine a saddle of a horse that goes that up, curved that way, and it curves, or the saddle of a mountain where two mountains join together. It goes both ways. It curves upwards and across.
Exactly. And what we'll look at next week is different versions of Pythagoras' theorem in the different geometries.
Oh my goodness. Okay. All right.
Okay, so that'll be interesting. And so I think our time is more or less up, and
Yes.
it's time to say goodbye. I will make this bigger again. And here we are. Happy Massa. And it's a goodbye from us. And there you see in one of those circles, you see Leonardo's picture, the picture of his proof. And also, I think we might make a remark about maths toys, Caroline. That's the name we give to our YouTube channel, the AimSet YouTube channel. And that's where you'll find these videos. Okay, so you have to go to, we'll give you the links, but you have to go to YouTube and then search for Maths Toys. And we named it Maths Toys because we're trying to promote the idea that you play with mathematics as with a toy, but you actually have something in your hands, a manipulative to, as you see in the tangram, making the boat there, or the pieces, as with Caroline showed us with Da Vinci's proof, you have pieces to rearrange, pieces of paper to fold or rearrange, or some other resource, some other manipulative, usually made from scrap material, to help you to understand the maths.
Thank you very much, Tony. We'll see you next week, and thank you for joining us. Bye-bye.
Goodbye.